Hey, this is Leach with Simpson Math, and in this video, we will be looking at what the world a factor is, and then how to find the greatest common factor of a polynomial. This is also part of a series of videos which will serve as a fundamental review of factoring geared towards the college algebra student. In these videos, I will show you how to factor using the AC method. So let's get started with finding the factor pairs of 24. So as we learned back in the day in elementary school, we should be able to find the factor pairs of 24. So 24 can be rewritten as 1 times 24, because any number can be rewritten as 1 times itself. 24 is also even, so that's 2 times 12, and then 3 times 8, and 4 times 6. So those are the factor pairs of 24. General tip, because we're going to be writing factor pairs when we factor trinomials, is I would always write them in this order. I would start with the 1 times 24 and then work on down the list. So that way on the left-hand side, you're kind of going up 1, 2, 3, 4, so forth. Now you might have to, do, depending on the number, you might skip something. So like if it's not even, you might have to do like 1, 3, whatever. But I always like to put my smaller numbers here in order, because then notice as you go down the list, the numbers on the right-hand side get smaller as well. So it's 24, big jump down to 12, big jump down to 8, less of a jump down to 6. And then notice that these two on the bottom get closer and closer and closer together. If this number was a perfect square, then this last pair would be the same number. Why is this helpful? Well, if you start looking for your factor pairs on this right-hand side with the bigger numbers, then you're going to be hunting and guessing a lot more. I like to start on the smaller side. And then if for some reason let's say I try 5 doesn't work, 24 is not a multiple of 5, so then I go, okay, well, what about 6? Oh yeah, it's 6 times 4, but 6 is already on my list. And once this happens, if I go down the small ones, and then once I get a number on the other side, I'm done searching. I don't need to try any other numbers. I know that I have them all. So that's my general tip. There's also some more helpful guides, helpful reasons later when we talk about factoring, because we'll be looking for a certain one of these. There's some more tips for that, but get used to writing your factor pairs this way. All right, so back in elementary school, you could have written your factor pairs as just like 1 and 24, 2 and 12, so forth. But what makes them be a factor? The big deal is that I am multiplying them together, multiplying them together, multiplying them together, so forth. All right, so let's look at so let's simplify 36/48 using this idea of the greatest common factor. Well, if I said, well, let's reduce 36/48, you might know that, well, they're both even, so you could try that. There's also 3s, there's also 4s. Ultimately, you should check and see that both 36 and 48 have a 12 in common. So the greatest common factor of 36 and 48, the biggest factor they have in common, is 12. So yes, 2s, 3s, 4s, 6s, all those would work, but 12s are the biggest. So the reason why that's helpful is because then we would reduce 12 over 12 is 1, and we're left with 3/4. You've known how to do that for a while. There's also something called prime factorization. It's a theory, a part of arithmetic that says that any integer can be broken down into its set of prime numbers. So just the big deal here for us today is that it's all about multiplication. So I can rewrite 72 as 2 times 2 times 2 times 3 times 3, or more efficiently, 2 cubed times 3 squared. So again, notice factoring, it's factorization, and it's all about that multiplication. So what does it mean to factor a number? Well, in my opinion, I would say it's to find the numbers that multiply together to get another number. So factoring is all about finding the things that multiply together. So from a previous thing we've looked at, finding 2x plus 5 and x plus 1. So 2x plus 5 times x plus 1, if we multiply those together, we end up with 2x squared plus 7x plus 5. And these two things are our factors. So these two items, so 2x plus 5 and x plus 1, those are multiplying together to get me that polynomial, that trinomial. These are factors. Same thing over here. If I have an x plus 9 times x minus 9, Well, that's x squared minus 81. So if I was to multiply those together to get this, I would get that. And these are factors. So what does it mean to factor a polynomial? Well, it means to find the polynomials that multiply together to get another polynomial. Another way of thinking about this, instead of terms of multiplication, so we're basically backwards distributing or unmultiplying, so division. So to find the factor, we're ultimately going to be dividing. But a factor, specifically, if I have two factors, that means I'm multiplying these two things together to produce that polynomial or to produce that number or whatever the thing is. So when you think factors, you need to think multiplication and division. So let's identify the greatest common factor among the terms in this list. So again, if you're freaked out like, ooh, there's three things, well, it's okay. So just imagine, so what is the greatest common factor of 8 and 24? So like, what if this was 8 over 24 and I said reduce it? Well, 8 and 24, well, they both have an 8 in common. That's the biggest. So that's that greatest common factor of those two. So basically, well, it's 8 so far, we're at the 8 and 24. But I could just then, let me test 24 and 52. Well, 52 does not have an 8 in it. If I do 8 times 6, I get 48. The next 8 would then be 56. So nope, 8 doesn't go into 52, but a 4 does. So the greatest common factor among those three numbers is 4. And you could check that because if I divide 8, 24, and 52 by 4, look at the numbers that's remaining. A 2, a 6, and a 13 are remaining. So does 2, 6, and 13 have any factors in common? Well, this 13 is a big dead giveaway, and so is this 2. 2 and 13 are prime, so they're not going to have any other numbers in common unless it's something bigger than them. So this, yes, 2 and 6 have something in common, but not all three of them. So just a little, well, what if you tried some other number? So if you looked at, let's say, 2. If you thought, well, 2 is a common factor, that is correct. I could divide 2 by all of them, but look at the remaining factors, 4, 12, and 26. They all have another 2 in them. They're all even, so I could divide another 2 out, so that's why we knew that there was something bigger. Well, what if you thought it was 8? I went through this a second ago. If you tried 8, notice 52 does not divide evenly by 8, so we would get 13 halves, so we know that that 8 is not correct or too big. All right, so that works for numbers. So it's the same idea. So let's look at the values x squared and negative xy. What would be the factors that they have in common there? Well, I could rewrite x squared as x times x. So when you look at it this way, the x squared has an x times x, and the negative xy has a negative, an x, and a y. So do they have anything in common? Well, they both have an x in common. So the GCF of these is x. So using that same division idea, I could divide an x out of x squared evenly, and then I could divide an x out of negative xy evenly. And if you look at what's left over, does x and negative y, do they have anything in common? No, they don't have anything in common. So that's how we can be confident that that is our GCF. Now, we're not just going to be finding GCF of values in the list. We're going to be dealing with them as polynomials. So let's find the GCF of these expressions and then factor it out. So that's factor it out. That factor is a verb then, how I use it that way, factor it out. So notice 8x plus 24y plus 52z. The 8, the 24, and the 52, those sound familiar. In fact, they were these numbers up here, so that's not a coincidence. So we already know what the GCF of those are because all I've added on were these variables, x, y, and z. X, y, and z, they don't have any common factors, so the GCF is just 4. So what I'm going to do is basically divide out a 4 from each of these. Divide a 4, divide a 4, divide a 4. But this is an expression. I can't just divide a 4 and call it a day, because if I actually divide a 4 from everything, I will change the value of this expression. So what I'm going to do is I'm going to kind of undistribute. Let me just jump to the answer. So notice, if I have 4 times this polynomial, I could distribute this into here. And if I do that, I would get 4 times 2x is 8x. Yeah. And then 4 times 6y is 24y. Yep. And then 4 times 13z is 52z. So notice, yeah, I get the same thing that I had up there. So the idea is I could produce division. I could go through division. So you can think 8x divided by 4 is what? Well, the 8 divided by 4 is 2. That x doesn't divide, so now I have 2x. And I continue that idea. 24y divided by 4 is, well, 24 divided by 4 is 6. And the 52 divided by 4, as we saw earlier, is 13, and the z sticks around. As I've said in previous lecture videos, anytime you factor out a GCF, make sure to do a quick mental double check. You don't have to write it down, but just do a quick double check to make sure that you factored it out correctly, especially if signs are changing, so be careful with that. All right, so let's take a look at this next one. So these are the same two values we saw in that list previously, but now they're just together. So separately, if I asked about those two terms, the GCF was x. So I have noted over here that my GCF, yep, is just x. So let's just factor or divide an x out of each. So if I divide an x out, one of the x's will reduce, and we're left with just an x. And if I divide an x out of here, those x's reduce to 1, and I'm left with a negative y. So there's my negative y. And then I have my x hanging out front. Again, anytime you do your GCF, just do a quick double check. X times x, yep, x squared. X times negative y is a negative xy. Yep, we're good to go. So that's how to factor that GCF out. All right, so here's some new ones that we haven't covered. I would like you to try this one on your own. So let's find the GCF. So the thing with this GCF, I'll give you one little tip, is if the leading value, if our first term, and do note that this polynomial is written in descending order of my exponents. There's an implied 1 for that exponent. So it's written in order. This is what we deem as the leading coefficient. If that first number is a negative, then you need to factor out a GCF that is also negative. So your GCF is also negative. So take a second if you want to and see what's the GCF of these terms. All right, so the GCF of these three terms is a negative 2x. Now when I do this, I like to do them separately. I like to think about the numbers and the variables, and if I have multiple variables, I'll look at each variable separately. So numbers first. Well, first, look at that big old leading negative. That's what this note says here, is that if the leading coefficient is negative, then my GCF is also negative. So negative. Now I'm going to forget about the negative and look at the values of the number. 4, 18, and 6. Well, can 4 go into all of them? Nope, 4 doesn't make it into 18 or 6. But I do notice that they are all even. So since they're all even, I can pull that 2 out. So they're all even. They don't have any other factors in common. So now let's take a look at the variables. I'm going to move on to the x. Forget about the numbers. I already have written down a negative 2 over here. So notice that they all three have at least one x. Do they have at least two x's? Nope, this one just has the one x to take out. If I take out any more, then it doesn't have any more to give. So I'm not going to do that. So my GCF is a negative 2x. So if you haven't done it yet, now that my GCF is negative 2x, I want you to factor out a negative 2x. So negative 2x parentheses, what goes in those parentheses? All right, so whenever you pulled out the negative 2x from each of these, sort of kind of again do it in stages. So I like to think about the numbers first. So if I divide a negative 2 out of negative 4, I'll end up with a positive 2. And if I take one of the x's out, then that x cubed will go down to an x squared. Remember that if I have x cubed divided by x, you just subtract them. So there's a 1 here. So this is really x cubed minus 1, which is x squared. All right, so I move on to the 18x squared. So what's 18 divided by negative 2? Well, first up, it's negative, so that sign's going to change. And then 18 divided by 2 is 9. And then again, just reduce the variable exponent by 1, and now we're at x. And then negative 6 divided by negative 2. Negative divided by negative is positive. 6 divided by 2 is 3. And then that x will reduce with that x, and we're left, it reduces with this x written that way. And so those x's reduce, and we're left with 3. So again, before you move on, just do a quick double check always. So write it down, write your answer down, and then do a mental distribution, just making sure that everything's good. If your GCF was negative, just do one more quick check and be like, I go, okay, negative, positive, negative, so they should swap. So now it's positive, negative, positive. Good, all the signs changed. It never hurts to be too sure. All right, so try this one on your own. All right, welcome back. So our GCF is a negative 3xy. So again, our the leading coefficient sign is negative, so we're going to pull out that negative. Pointing to the wrong thing. We're going to pull out that negative. Then let's compare 3 and 6. They have a 3 in common, so I'm going to pull that 3 out. Not 6, because that wouldn't work there. They both have an x, and they both have a y. They don't have more than one x. This one has 2 of them. This one only has 1. So my GCF is a negative 3xy. Now, when you factor out that negative 3xy, we end up with this. Some students get tripped up by that. Remember, we are dividing. So what is a negative 3xy divided by negative 3xy? Well, negative reduces, 3 is reduced to 1, x is reduced to 1, y is reduced to 1. They all reduce to 1. That 1 sticks around. And then again, when you do this over here, negative 6 divided by negative 3 is positive 2. The y is reduced to 1 completely, but we'll be left behind with one of the x's. So again, this is why I implore you, anytime you do a GCF, just do a quick double check of a distribution. Because I've had lots of students, I've taught this lots of times, and they don't want to include the 1. They're like, well, it just disappeared. Remember why I'm picky about how 6 minus 6 cancels to 0, but 6 divided by 6 reduces to 1? The reason why that is because they're right here. And also then do a distribution double check. So if I was to distribute this, do I end up with what I previously had? Yes, because this is negative 3xy times 1, which will give me that negative 3xy. But if I didn't have this, and you probably wouldn't have written the plus, then you just have negative 3xy times 2x. Distribute that. Yeah, you just have this. You just have negative 6x squared y. So you do notice notice that if you don't have that 1 plus, then you don't have this first term at all when you do your double check. That's why that's so important and so helpful. All right, so if your GCF is an entire one of your terms, when you factor it out, make sure that we leave a 1. All right, so this section I'm calling just quick fire. So just 6 questions you can just try on your own. I'm going to reveal them all and just talk about some highlights. I'm not going to go through each and every one of them. So try these GCFs on your own. All right, welcome back. Let's see how you did. So in this first one, it's just a 9 that pulls out. So you just pull out a 9, you have a y minus 4 left inside. This one again, your leading coefficient has a negative, so your GCF also needs to be negative, and so we end up with this. Over here, again, just making sure that we're good with those 1s that are left behind. Hopefully you got that right. Over here, we have a 6x that comes out, leaving this trinomial. All that we have going on in this last one, or these last two, this one is a negative because there's no x's in common. This is a 1, this is a 3, this is a 5, nothing in common except that leading negative. So pull out that leading negative, and then everything else just changes signs. But this last one, there's nothing in common. 3 and 5, nope, this is x squared, this is no variables, not even a leading negative. So it's what we would call prime. So if you see a polynomial that has no factors, In this case, we're just looking at GCFs, but it has no factors other than itself, then it's a prime polynomial. Right, so after this video, you should know what a factor is, and then also you should feel comfortable with GCF. The big deal with this GCF is that on this series of videos, every single time you start a problem, the first step is to factoring out a GCF. First step, step one, factoring out a GCF. So make sure that we're good with this, and then I will see you in the next video when we talk more about a special case of GCF.